Okay, we're going to start our talk about matrices and determinants by looking at using matrices to help us solve systems of linear equations, particularly systems that have more than two variables. Our objectives are to write a matrix in the appropriate format in order to use the calculator to do these operations. We're going to also do some manual operations to perform elementary row operations so that you understand what the calculator is doing. And then we'll, of course, use the matrices to solve systems. First order of business is to identify the dimensions or the size of a matrix. We name matrices based on the number of rows and number of columns that they have. So in this example, if we count our rows, we've got 1, 2, 3, 4 rows. We've got 3 columns, so therefore we call it a 4 by 3 matrix. That's pretty straightforward. Okay. We can also refer to each of the elements, and each of the numbers in a matrix are known as an element. And we could refer to a specific one by using a subscript. So in this example, A sub 2, 3 means the number that is in matrix A, row 2, column 3. Okay, so that would be the second row, which is this one, and the third column is this one. The number that is there is 0. So we would say A sub 2, 3 equals 0. Now we need to be able to create what's called an augmented matrix based on a system of linear equations. And the important thing is to be orderly. If you look at this system, we've got 4 variables, w, x, y, and z. Not every variable is in every equation, but that's okay. We need to account for them all. We have 4 equations, which is good because we have 4 variables, and we would need that in order to be able to solve the system. What we need to do is organize it, though. Notice that they're not all in the same order. This one is X, Y, W. This one is Y, Z, W. The best bet is to put them in alphabetic order and just rewrite this. So I'm going to quickly do that. And let's just start with our W. This is going to be negative W plus X plus 3Y. There's no Z equals 9. This one will be 2W minus Y, no X, plus 4z equals negative 2. This is x, negative 6w. Let's fix that. Let's just rewrite that. Just cross that out. Negative 6w plus x minus 5z. I don't know what is going on with this pen. I apologize. Equals 0. And this is no x, no w, 2x plus 4y minus 3z equals 4. And what we're going to do is we're going to create a matrix. And the numbers in the matrix are going to come from the coefficients of each of these variables and the constant term here. Okay, so the first row of our matrix, let's just draw a matrix here. The coefficient of w is negative 1. Of x is 1. Of y is 3. Of z is 0. And the constant is 9. That's the first row. Okay, here we're going to have a coefficient of w, again, it's 2. Our coefficient of x is 0. Y is negative 1. Oops. Z is 4. And the constant is negative 2. Here we have x is, we have w, negative 6. X is 1. Y is 0. Z is negative 5. And the constant is 0. And then we have 0, 2, 4, negative 3, and 4. The important thing is to put those zeros in the right places. If a variable is not represented in the equation, just put a 0 in. So this is our matrix. It has 4 rows and 5 columns. So it is a 4 by 5 matrix. Oops. I can spell. 4 by 5 matrix. So we can do some of these calculations manually, although it does get a little bit lengthy. I'm going to take you through part of one of them. We would do it by doing elementary row operations, and by that I mean we can interchange two rows, we can multiply a row by a constant, or we could add one row or subtract a row from another row. Okay. So here we have a system, and what I'm really trying to do is create a system that has zeros down in the bottom left. Okay, so I want this to be, this first equation could have x, y, and z. The second equation, I just want to have y and z in it, in the constant. And the third equation, I just want to have z in. Okay. So if I look at this, if I add the first two equations, I'm going to drop out the x. All right, so my first equation would stay. It would be x minus 2y plus 3z equals 9. And if I add the two together, my next one has no x's. Y is going to be just 1y. Z is going to be 3z. And 9 plus negative 4 is 5. Okay, so now I've reduced the x. I've gotten rid of the x in the second equation. That's good. What I'd like to do is have a third equation that doesn't have either x or y. So what I could start off by doing is multiplying this by 2 and adding these two together. That'll get rid of the x's there. So let's do that. It's going to be no x's. I've got 6x plus negative 5y is just y again. And 2 times 0z is 0z plus 5z is plus 5z equals negative 8 plus 17 is 9. Okay, so now I still don't have this last equation in terms of only z, but I could easily get it there by subtracting the second equation minus the third one. So I'm going to do that, and I would get the y's would cancel. I get 3z minus 5z is negative 2z equals, and 5 minus 9 is negative 4. Okay, so now I've got equations that have all three variables, two variables, and just the one variable, and I can do what's called a back substitution, which means that first thing I could do in this bottom equation, I could solve that for z very easily, and that would be z equals 2. And then I can go back into one of my other equations, y plus 3z equals 5. Well, that would be y plus 3 times 2 equals 5. Or y plus 6 equals 5, or y equals negative 1. And then I can go back to my first equation and back substitute again. I know the value of y, I know the value of z. I could then go back to this equation, plug in y and z, and figure out what x is. And by that method, I've solved my entire system of equations. The good news is that we don't really need to do this manually. We can do it on the calculator. We're going to use something called reduced row echelon form on the calculator. And all that means is it's a matrix, if I have a simple matrix, that has numbers like this: 1, 0, 0, 2, 0, 1, 0, 5, 0, 0, 1, 1. Okay, something like that. In essence, all you have, except for this last column, you have ones on the diagonal. Okay, and the way we're going to interpret this is if this was a system of equations with the variables x, y, and z in that order, then this would mean 1x equals 2, 1y equals 5, and 1z equals 1. So you can see that your solution pops right out of the matrix once you have it in this reduced row echelon form, which the calculator will do for us. Okay, so we're going to go ahead and solve this system, and we're going to use the calculator. The first thing we need to do is organize it. It needs to be all in the same order, and this one starts with a y, this one starts with an x. I don't know if that's really good. I'm going to go right to rewriting this, x, y, z. It looks like x, y, z, w, y, z, w. It's actually in the order x, y, z, and then w for some reason, which is okay to leave it that way. We just need to keep track of what order we're in. So we can go ahead and create our matrix. Okay. And our matrix is going to be the coefficients. Okay, well, the coefficient of x here is 0. There's no x in the first equation. Okay, so I'm going to put a 0 there. Then y is 1, -2, and that's equal to -3. Did I miss something here? 1? I missed a 1, right? Y and z. All right, bear with me. Let's undo. Okay, x is 0, y is 1, z is 1. 0, y is 1, z is 1. I missed that. W is -2, and our constant is -3. Okay. Here we start off with x as 1, y is 2, z -1, w is not there, and the constant is 2. 2, 4, 1, -3, -2, and 1, -4, -7, -1, and -19. Okay. So that's the matrix. I'm going to stop this video here and pick up on the next one with putting this matrix into the calculator and using the calculator to solve the system for us.